Hi, everybody. This is Dr. Nigro with the Chem Calculations screencast. The screencast is going to focus on general spectroscopic techniques. What is it? What do we use it for? What are some specific ones that we are going to look at in AP Chem? I am going to have separate screencasts for each one of these techniques, which is going to have a little bit more detail, and in particular, talk more about the spectra that are produced by these techniques and how to use them and analyze them. So make sure you go look at each one if there's a particular technique that you're interested in. But this is more of a general overview, an intro, if you will. All right, so what is spectroscopy? Spectroscopy is the study of the interaction between electromagnetic radiation, which is also known as light, and matter. All right, so it's pretty straightforward. How does energy in the form of electromagnetic radiation affect atoms? How does it affect the atoms individually? How does it affect bonds within molecules? How does it affect interactions between molecules? What does matter utilize this absorbed energy to do within those atoms and within those molecules? All right, now there are many different spectroscopic techniques. They get categorized into a couple different categories. We are going to focus on techniques that are absorption or transmission of that energy, that electromagnetic radiation. All right. So, in other words, the energy is not going to be produced by the atoms and the molecules and emitted out. Instead, we're going to irradiate or shine light of particular wavelengths or a set of wavelengths on our matter and then observe what energy is being absorbed and what that energy is being used for, or what energy is not being absorbed, what is being transmitted through our sample. All right. The other techniques include emission spectroscopy, where energy is released by our molecules. And what does that tell us? There's other techniques called scattering techniques, where you irradiate and you look at what bounces off of your sample. But those two sets, those two classes of techniques are a little bit outside of the scope for AP chemistry. Again, if you carry on with chemistry or any sort of STEM science in college, you probably are going to run up against some of those. All right. But we are going to focus on absorption transmission type techniques. All right. So, what this really is the measurement of the amount of light that is absorbed or transmitted by a sample. And usually this is as a function of the wavelength of that light. All right. So if you think about it, when light passes through matter, oops, certain wavelengths are absorbed and others are not. All right. So when energy is absorbed, what is the atom doing with it, or what is the molecule doing with it? So that absorbed energy causes, whoops, electronic transitions within atoms or impacts molecular bonds. All right. Now, what that energy can do depends a little bit on what the energy of, or sorry, what the value of energy that light is possessing. All right. So, in other words, if you remember our formulas, we learned that energy is inversely related to the wavelength of light. So, as the wavelength increases, that means the energy that that light possesses is decreasing. All right. So that energy value impacts what that light can do within your sample. All right. If you think about it, if you use something, let's say, let's go way up there, gamma rays. All right. Very short wavelengths, but very high energy. Those gamma rays probably have enough energy to break bonds within molecules. So if you irradiate something that contains a molecule, you could break that molecule into small pieces, which you can then analyze. All right. If instead you took something like radio waves, those radio waves have very long wavelengths, which means very low energy. They may not be able to do very much outside of make the molecule move a little bit, but they aren't going to be able to break bonds. They probably don't have the energy needed to make electrons move around within your atoms. All right. So as you increase the energy of the light that you're irradiating your substance with, you basically can dig deeper and deeper into that molecule and into the atoms and cause things to happen. All right. But the energy value of your radiation is going to be very important as to what it can do. And that informs the different techniques that we can utilize. All right. Now, for most of these techniques, you're going to get what's called a spectrum. All right. And that spectrum is going to have peaks or valleys, depending on what it is looking at. All right. And the intensity of those peaks or valleys gives us a look at the concentration of that particular substance. All right. So if you have a sample that's very dilute, you might get a peak due to a particular wavelength that's very small. But if you triple the concentration of that substance, the peak will be in the same spot, but it will be 3 times as intense. All right. So we can use the height of the peaks or the valleys to determine how much of a substance is there as well. So that's another way that we can utilize these techniques as a way to look at concentration, which we do a lot. All right. So these are 3 of the 4. I'll talk about the fourth one. It wasn't on this slide, but I did like this little table. All right. The first one that we're going to talk about is infrared, also known as IR spectroscopy. All right, so infrared has wavelengths around 10 to the negative fifth meters. If you look up at your EM spectrum, right, it's on the lower end in terms of energy. So we're probably not going to be able to break bonds with this. And in fact, what it can do is as that energy is absorbed by your molecules, it causes those molecules to vibrate. All right, in particular, it causes the bonds within the molecules to stretch and to bend. All right. So there's no breaking of those bonds, but there is motion of those bonds. All right. And different bonds will interact with this energy differently. All right. If you can imagine, a double bond is going to be harder to stretch than a single, and a triple bond is even harder to stretch. All right. So you're going to need different values of energy to make those move, which means that their spectra are going to look very different. So it lets us look at the different bond types that are present within our molecule. All right. Up next, we have ultraviolet visible spectroscopy, also often called UV vis spectroscopy. You can see that our wavelength has gone down. We went from 10 to the negative fifth meters. Now we're at 10 to the negative eighth meters. All right. So our energy value has gone up, which means that this radiation could do a little bit more. All right. What UV vis is good for is making electrons within their atoms in our molecule jump to a higher excited level and then drop back down. All right. So the electrons get promoted to a higher energy state, and then we can monitor what energy is needed to make that happen. All right. Now, for single atoms, it's pretty straightforward. We get our atomic spectra. But for molecules, it gets a little more complicated because we have overlapped hybrid orbitals, which have different requirements for energy jumps. All right. So it's going to get very complicated when it comes to molecules. But in the end, we can determine in general what types of bonds might be there. We can also identify if a molecule has some sort of metal present. A lot of biochemical proteins in particular have metals involved. All right. And we can look in specific how those atoms are interacting with each other. All right. Now, the last one on this table is called mass spectrometry, all right, also known as mass spec or MS. Now, the first thing to look at is the non-spectroscopic technique. So what does that mean? All right, well, it means that it's not dealing with the interaction of light and our sample. Mass spec is a different technique. It looks at charge and magnets, and we're going to talk about that in a separate video. All right. But it gets grouped in here because it is one of the basic techniques that we use when analyzing molecules. All right. What it does is, for our purposes, it's going to let us look at isotopes for a particular element. If you move on to organic chemistry, it is a very powerful tool for looking at fragments of molecules, and it allows you to build those molecules back from those fragments. All right. So if we think about what we've got here in terms of energy, all right, that increasing energy, we've got infrared, which is going to have less than our UV vis energy, which is why we get bond vibrations, all right, only for that IR, no electron transitions. All right. Whereas for our UV vis, we have more energy. All right. So now we get electron transitions. All right. And that is within the atoms for our purposes. All right. And this is going to vary by what elements you're looking at and their environment. And by environment, I mean, what are they attached to? All right. Now, one that is not on here, one technique that's not on here, which I wish was, but it's not. All right. It's called photoelectron spectroscopy. All right. This is also sometimes called PES. All right. This is higher energy than UV vis, although there is some overlap. It depends on the element. I want to be very clear that these are not set boundaries, right? There's overlap between all of this. It depends on the element, depends on the environment. All right. But because it is generally higher energy than UV vis, if UV vis energy was able to promote electrons to an excited state, all right, then even higher energy, this leads to full electron ejection from the atom. All right. So if you think about it, as you increase the energy, you start out with the valence electrons, you can remove those. And then if you irradiate with even higher energy, you can start to remove core electrons as well. All right. So we're going to see when we talk about photoelectron spectroscopy specifically, it's all about determining the electron configuration of our atoms. All right. But it does vary by element. All right. And similar to our other techniques, you can also focus on molecules, and you can split molecules in part by breaking bonds. But that's, again, outside of our scope. All right. Now, here I have what is a general setup for any sort of spectroscopic technique. Each one will have its own quirks. There are going to be mirrors, there can be focuses, there can be lenses. All right. But generally speaking, you need to have these parts somewhere within it. All right. Your light source. All right. This is your energy source. All right. Now it could be a multi-wavelength source, or maybe it's a laser which has one particular wavelength. All right. But it's going to get focused through a lens, and then that lens goes through some sort of prism or grating. All right. And what that lets you do is split into your various wavelengths. All right. So it allows you to choose what wavelength you want to focus on by splitting that light into its discrete wavelengths. All right. Now your slit lets you focus in on a wavelength. All right. Now maybe your experiment is set up to choose one wavelength, or maybe it's called a scanning technique where you look at a multitude of wavelengths. All right. Either way, all right, the monochromator allows you to split it into the wavelengths, and then you can choose using a slit whether you want one or a bunch. All right. The key though is that the light then shines through. Whoops, sorry. What happened there? The light then shines through your sample, which is in some sort of cuvette. All right. And within this cuvette, there's going to be a path length. It's usually 1 centimeter. Most of the cuvettes that we use in lab are going to be 1 centimeter, but can be smaller. All right, just depends. And this is going to be IO is the light before it goes through, and IT is after. All right, and so your detector then is going to look at the difference. All right, whatever is missing, that is what got absorbed by your sample. Okay, all right, so that digital meter is going to read the difference between IO and IT. All right. So generally speaking, we call that the transmittance, which is T, which is going to be equal to IT divided by I. Oh, now we don't tend to do the calculations. We let the machine do that for us, but that is what it is measuring, is what got through. Okay. All right, so like I said, this is a very general intro to spectroscopy. All right, we are going to look separately in different screencasts at IR spectroscopy, at UV vis spectroscopy, at PES spectroscopy, and then at mass spec. So if you have a specific technique you would like to look more at, please go look for those techniques, those screencasts. All right, but keep in mind that they all look at the study of the interaction of electromagnetic radiation and matter, and that the wavelength of that light tells us what the energy of that light is, and the energy value is what determines what it can do when it interacts with the matter. Right? Can it make bonds vibrate? Can it break bonds? Can it make electrons move to excited levels, or can it fully eject those electrons from the atom? Right? All of that depends on what the element is, what the bonding environment is around it, and what the energy of that radiation is.